Greetings, my name is Guilherme, and I'm going to present a hypersonic vehicle design for stratospheric flight. This work was possible thanks to the collaboration between the Universidade Federal de Santa Maria and the Universidade Federal do Rio Grande do Norte, by the authors myself, Marcelo Zanetti, João Marques, Jorge Marinho, Pedro Araújo, e Paulo Turo. The way human beings access space today is by rocket engine. This type of technology uses liquid or solid propulsion inside the vehicle, so the rocket carries both fuel and the oxidizer. And because it carries the propellant in addition to the fuel, a small amount of mass remains for the payload. Since around 90% of the vehicle's weight during takeoff is due to the propulsion and structure systems. Therefore, it is very expensive to use a rocket engine. Being aware of this, we need a new technology to achieve hypersonic speeds that is more coherent, less expensive. One way is accelerated propulsion, that is to use the atmospheric air itself as a propellant, so you won't have to carry the oxidizer inside the vehicle anymore, because the air is full of hydrogen, which can be burned to generate impulse of the aircraft. The idea of hypersonic aspirated propulsion is to use the shock waves that are generated by the high speed of the vehicle in its geometry to compress the air, so that it is burned in the combustion chamber. If the temperature of the air in the combustion chamber increases so much because of compressions, so that it is greater than the ignition temperature of the fuel, for hydrogen it is 8045 Kelvin, and the flow remains supersonic in the combustion chamber, then supersonic combustion is possible and will certainly happen if hydrogen is injected. For us to design a hypersonic vehicle, we need four main considerations. The oscillatory criterion, which will allow us to calculate the slope of the ramps in the compression section based on the maximum recovery pressure, considering that all shock waves generated by each compression ramp fall on the same point on the leading edge of the fairing, and there is only one reflected shock wave that will fall on the edges of the combustion zone. In other words, considering shock on lip and shock on corner. So this oscillatory criterion says that for the recovery pressure to be maximum, the angles have to describe a law, which is the sine of the angle between the shock wave and the reference line times the Mach number has to be equal for all ramps, which is equivalent to saying that the normal component of the velocity remains constant through the shock wave. The second theory is the oblique shock wave theory, which is the theory that will calculate the properties of the flow during compressions. So the air in front of the vehicle at free stream will go through the first shock wave, and this theory will allow us to calculate the thermodynamic and dynamic properties of the flow. The thermodynamic properties will increase when the flow passes through the shock wave. That is, pressure, temperature, and density will increase, while the dynamics properties will decrease. That is, Mach number and velocity will decrease. Then, in the combustion chamber, we have the Rayleigh theory, which is a theory that describes the flow with added heat. That is, this theory allows us to calculate the flow properties when heat is added. In this case, when hydrogen is added and the flow temperature is greater than the fuel ignition temperature, the fluid will burn, adding heat to the flow, and therefore modifying the properties of the air. Rayleigh theory says that whenever heat is added to a flow, it tends to reach sonic velocity, Mach number 1. In our case, as it is supersonic, the Mach number of the flow will decrease in the combustion chamber. If there is burning fuel, power on. So, for example, if you get Mach number 2 at the entrance of the combustion chamber, we can add as much heat as we want to reduce the Mach number as much as you want, as long as it is greater than 1. So we can put an X amount of heat to put the Mach number at 1.1, just like we did on the paper. And the last part of the vehicle's trailing edge, which we use the Prentice-Meyer and area ratio theory. These theories will allow us to calculate the thermodynamic and the dynamics flow properties in the expansion fan, in the expansion section. So we calculated two scramjet configurations. The first with the angles described here, flying at 23 kilometers with Mach number 5.8. And the second one, flying at 30 kilometers, Mach 6.8, with these angles here, calculated by the Ausbach criterion. Here's a table for the power-on case, burning hydrogen through the scramjet flying at 30 kilometers of altitude. We made several tables, one for each case. In this table of the example, we see here the properties of the air at 30 kilometers of the altitude, which we got from the US standard atmosphere. From the air at free stream, we calculate the flow properties from the first shock wave. So here, look. The pressure increases, the temperature increases, the density increases, the sound velocity increases because it is an exclusive function of temperature. And the flow velocity decreases and the total temperature remains constant. So the thermodynamic properties increases and the dynamic properties decreases. The total temperature remains constant because of the conservation of the energy law. So I do this for all ramps, first, second, and third ramps. And here we got the reflection zone. Since it's shock and shock and core, the reflection angle has to be the sum of the compression angles. And we can calculate the flow properties through the reflection angle, and we got these results. We can see here that the temperature at the entrance of the combustion chamber is 1092 Kelvin, which is greater than the ignition temperature of the hydrogen. So it will burn the hydrogen. So thus, Mach number 2.37, the flow is supersonic in the combustion chamber. Temperature 1092 Kelvin, greater than 8035 Kelvin. There will occur supersonic combustion. In this case, we added heat, we added hydrogen. So we can see here in the combustion section, it enters with 2.37, and we add the heat sufficient to make the flow exceed with 1.1 Mach number. So calculating the properties of the flow for this, we have the pressure increases, temperature increases, density increases, the flow velocity decreases, the sound velocity increases since the temperature increases. The total temperature increases because we added heat. And here in section 10, after the expansion, it goes with Mach number 1.1 and exceeds with Mach number 6.66. And what happens in the combustion zone is the opposite of what happens in the compression zone. Thermodynamic properties decrease and dynamics properties increase. So we see that the pressure drops, the temperature decreases, the density decreases, the velocity of the air decreases because the temperature decreases, and the sound and the velocity of the flow increases. We note here that the flow velocity at the vehicle's trailing edge is greater than the air velocity at the beginning, which makes sense because the scramjet with power on is pushing the air that is flying forward, that is impulse generation. For the case of power off, we saw, and it really has to be that way, that the flow velocity after expansion has to be lower than of the free stream, because in this case, it doesn't matter, it doesn't make sense for the scramjet to be moving forward without any form of impulse generation. Therefore, a scramjet design is being developed at the Universidade Federal de Santa Maria with the intent to demonstrate the supersonic combustion. So far, it was acknowledged that the study's configurations were capable of generating net thrust for the aircraft. The authors would like to thank the Universidade Federal de Santa Maria, Universidade Federal do Rio Grande do Norte, and the CAPES Foundation for financing this project. Thank you for the attention.